Hello everyone and welcome to the Brainy Founder channel. Lifespan, Why We Age and Why We Don't Have to by David A. Sinclair, PhD, offers a scientific explication of the aging process and propounds a rather provocative idea that aging is not necessarily an inevitable part of life, but rather a condition that can be treated. How Sinclair, one of the world's leading researchers, proves the causes of aging on genetic and molecular levels offer breakthroughs in biotechnology and medicine to slow, stop, or reverse the process of aging. In this book, there are more hopeful visions of aging. Now, a future prospect of extraordinary longer lives and health span is brought to focus. Sinclair discusses the way this could also give rise to serious ethical and societal issues and asks for a critical redefinition of what it means to age in breathtakingly fast-moving times. Chapter 1: A Grand Unified Theory of Aging, a very brief overview. In the very first chapter, David Sinclair surprises the reader with his highly unconventional view of aging. He begins by debunking the age-old belief that aging is part of nature and there is nothing anyone can do about it. On the contrary, he refers to it as a disease, something one supposes can be treated, managed, and cured. The idea forms the theme for the whole book, as Sinclair argues that there is potential to significantly extend both human lifespan and health span by working on the understanding and manipulation of biological processes underlying aging. Central to Sinclair's case is the information theory of aging. He uses an extended comparison between human aging and a computer system. In the analogy, the entire suite of genes in a cell, known as the genome, acts as the hardware, while the epigenome, or the system that dictates which genes are on or off, acts as the software. As time moves on, the epigenome gets corrupted, like how software can collect mistakes and viruses. It's this corruption that makes for the loss of information the cells need to function properly, resulting in the different diseases and symptoms associated with aging. Sinclair says that what keeps cells in appropriate identity and function is through the epigenome, ensuring that the right genes are on at the right times. With age comes loss of that fine control, the epigenetic noise. Thereafter, it is this epigenetic noise that gives rise to a cell's loss of identity and malfunctioning, thus causally leading to the aging process. For example, parts of our skin cells forget the fact that they are skin cells. As a result, wrinkles occur in these places and elasticity is lost. Other cells might start misbehaving, triggering cancer or other age-linked diseases. The chapter places an important focus on the sirtuin family of proteins, which have high relevance to the aging process. Sometimes referred to as guardians of the genome, sirtuins are involved in stabilizing and maintaining the integrity of the epigenome. They perform this function through DNA repair and the gene expression regulation to ensure cells are functioning correctly. Sinclair describes how sirtuins are activated on stress, such as caloric restriction or exercise, to have a pro-longevity effect. He further identifies the exciting fact that sirtuins seem to be highly conserved from yeast to humans and thus may play a core role in the biology of aging. Activating sirtuins in yeast can extend life up to 30%. Such a discovery has fueled further research on whether sirtuins may be harnessed to delay the aging process in humans. Another critical aspect of this theory of aging is the role played by DNA damage. Every day, our cells are under severe attack from a variety of factors causing DNA damage, whether from UV through radiation, various environmental toxins, or metabolic byproducts. Although the cells have mechanisms to repair this damage, it is not perfect. Hence, errors can accumulate over time. Sinclair likens it to when a compact disc gets scratched. Such errors in playing occur with this CD, similar to what happens to DNA with aging. These errors in the DNA disrupt normal cellular functions, contributing to aging. However, Sinclair points out that it is not the mere accrual of damages in DNA that explains the elderly process. It is rather a manner of a cellular responding to this damage, precisely how the epigenome gets disrupted during repair, which has been accelerating its process of aging. Sirtuins repair the DNA at the cost of properly handling the gene expression, just as they are called to tasks. The net effect of this instability over time results in a loss of cellular identity and function that is perceived as aging. One of the most exciting ideas to arise in this chapter is the possibility that age can, in effect, be reversed by restoring some of the lost information within the epigenome. Sinclair discusses experiments where the epigenome of aged cells was partially reset, rolling back the biological clock. It was accomplished through the re-expression of some genes which epitope silencing due to epigenetic noise had fallen silent, thus providing a regain of their youth functions to such cells. Though this research is still in an incipient stage, the results derive far-reaching implications. If scientists could find a way of doing so safely and effectively in humans, to reset the epigenome would be treatments not only arresting but reversing aging. This represents one of the monumental shifts in medicine, transforming the way age-related diseases are approached and possibly extending a human life by decades. Finally, Sinclair wraps up the chapter by calling for further research into the mechanisms of aging. We are, he says, on the threshold of quite a different kind of medicine, one where aging will not be seen as a necessary decline, but merely one more manageable and treatable condition. The keys for this future lie in the understanding and manipulation of the epigenome, harnessing the power of sirtuins and finding ways to repair or reset those biological systems that go awry with age. He also speaks about the ethical and social problems arising from this development in relation to the science with the extension of life. He says that when there is a kind of immortality in sight, questions arise relevant to the future of humanity, how society is slowly going to adapt to maybe more extended life, and the implications of tampering with something as basic as aging. These are questions to be posed as the science gets perfected. Chapter 2: Longevity Now. Chapter 2 of David Sinclair discusses the current progress in longevity research, emphasizing that a longer and healthier life is no more fiction than it is real and already within reach. He revisits some formidable scientific breakthroughs already made toward this goal and discusses the practical strategies any individual can undertake right now to improve health span, the period of life spent in good health. The chapter thus enables review of the recent scientific advances as a guide to the adoption of lifestyle practices supporting longevity. One of the key topics Sinclair writes about in this chapter is that caloric restriction has long been documented as a method to extend the lifespan across most species. He says that what caloric restriction does is it activates survival pathways in the body that increase cellular repair and maintenance, thereby slowing the process of aging. Said another way, because humans' bodies recognize there is a shortage of food, they go into survival mode by upregulating processes that are conducive to the preservation and protection of cells. Sinclair also talked about fasting, which is an easier way of creating a caloric restriction for most people. Intermittent fasting is the process that takes place in the cycles of eating and fasting. This accomplishes what would otherwise be achieved with long-term caloric restriction without having to continually diet. He refers to the mounting data indicating it can improve metabolic health, reduce inflammation, and enhance self-repair in the body. Exercise is another core aspect of Sinclair's longevity approach. He stresses that regular exercise performs one of the best ways of promoting a long and healthy life. Exercise itself turns on many of the same pathways as caloric restriction does in cellular repair and stress resistance. He describes at great length the many advantages of both aerobic exercise, that which ensures good cardiovascular health, and resistance exercise, which sustains the mass and strength of muscles with age. Exercise will favor the production of molecules like brain-derived neurotrophic factor, a molecule supporting brain health and likely protecting against neurodegenerative diseases. Another major focus of this chapter is diet. One of the factors Sinclair favors is a diet mainly based on plants, for which contributing factors have been variably associated with health benefits associated with reducing the risk of chronic diseases and extending life expectancy. His argument is that plant-based diets are investor-rich in polyphenols, products found in plants that produce antioxidant, anti-inflammatory activity, and as such may activate the pathways associated with longevity in response to the two main exposure variables being discussed, CR and exercise. He does, however, remark on a few dietary supplements that may have a value when it comes to longevity. For example, he likes resveratrol, the constituent of red wine he discovers to switch on sirtuins, which are those very proteins involved in regime prolongé, discussed in Chapter 1. Though still emerging with the evidence for resveratrol and other supplements, Sinclair argues that they might form just one part of a more general strategy for improving health span. One key element in this chapter is hormesis, which represents small doses or minor stresses that have a limited beneficial effect on the organism. Sinclair explains how small exposure to stressors, be it fasting, exercise, or certain plant compounds, induces an adaptive response that gives new positive changes for resilience and longevity to the body. Comparing hormesis to the saying, "What doesn't kill you makes you stronger," Sinclair explains that it is possible to stimulate the pathways that will help protect against aging by putting the body under manageable levels of stress. An example he gives is of the way it works at a cellular level, hormesis causing the activation of autophagy, a process by which cells clean out damaged components and recycle them for energy. Through the chapter, Sinclair really hammers home that while all this science is very promising, there are concrete acts one could do today to live long. He implores readers to lead a life full of exercise and balanced food, full of plant-based foods, with periods of fasting or caloric restriction. Sinclair also advises to keep track of the newest results regarding longevity science research. New findings are being made all the time. He clearly states that not all the strategies discussed would work for everyone, but obviously some of them surely can be found to sustain the systems working in any given individual. Finally, Sinclair sets the final touches to this chapter. He shared his views about future prospects with regard to longevity science. The author is greatly optimistic that further elongation of human lifespan might be facilitated with the new types of therapies and interventions that will be devised in the near future. He also added that much more research was needed to know exactly how aging works and how best to target it. He envisages a future of personalization in treatments for longevity based on one's genetic heritage, lifestyle, and environment. Sinclair foresees that the more the science of aging evolves, the better and more accessible strategies will be found for long, healthy lives. Chapter 3: The Epigenetic Clock. And Chapter 3 pushes even deeper into the conversation about the epigenetic clock, not just as a revolutionary new form of biomarker for measuring someone's biological age based on genome-wide DNA methylation patterns, but one that's literally able to predict lifespan and track aging at a molecular level, showing an accurate picture of exactly how old somebody is above and beyond the actual number of years that have passed in human life. A biological model underlying the proposed epigenetic clock comes from the fact that during the process of aging, there is a particular pattern of changes in DNA methylation, specifically attachment of methyl groups around DNA molecules, usually acting as an epigenetic mark of gene silencing processes. These aren't random events, and as a result, they follow a particular pattern that can be modeled into a description of biological age. The chronological age differs from the biological age. A person's chronological age is calculated by the number of years he has lived, while one's biological age is determined by the condition of his body and how fast he is aging, explains Sinclair. Sinclair highlights the work of one Dr. Steve Horvath, one of the scientists behind the very first accurate epigenetic clocks. A Horvath clock is able to estimate biological age to a few years of chronological age, considering the patterns of methylation taking place at particular sites in the genome. This tool has grown to become extremely instrumental in reinforcing research into aging and will be of testing many interventions' effects on biological age, as well as gaining insights into the mechanisms that drive such experiments. Early, on the other hand, the biological age estimated from the epigenetic clock is said to be one of the critical predictors for general health and longevity. Sinclair adds to this information by saying there are studies that have shown a very tight association between biological age and the risk of disease, including diseases of cardiovascular origin, cancer, and Alzheimer's. Those people who have a biological age younger than their chronological one have been found to live longer and with lesser disability, while people with an older biological age are at an increased danger to get ill and more prone to premature death. As Sinclair explains, the epigenetic clock comes forward as very important not just to predict span of life, but to see right through the base aging process. By getting a grip on whatever factor or factors drive changes in DNA methylation over years, scientists think they might begin to unlock the secrets of the aging process and eventually set the stage for interventions to slow, or for that matter, turn it into reverse. What is potentially the most exciting aspect of the chapter is the ability of new treatments to reverse the epigenetic clock. Sinclair makes the inference that, because aging is partially a result of accumulated epigenetic changes, the reversal of these changes will actually set the biological clock running backward and reset cells to a more juvenile state. He goes on to describe such experiments where scientists have already partially achieved a reset of the epigenome of the cell, thereby rejuvenating it. He later described experiments in which they treated old mice through the in vitro application of reprogramming factors, which indeed achieved the biological age reversal by quite a wonderful margin. In those experiments, besides staying healthier, old mice actually started regrowing tissues and muscles. The results imply that it might be possible not just to halt the process of aging, but to actually reverse it through treatments targeting the epigenome. Whereas DNA methylation is one of the prime mechanisms of gene regulation, its dysregulation turns out to be a hallmark of aging. As Sinclair explains, the epigenome profile becomes more noisy with age, resulting in gene dysregulation that would be well controlled if not for aging. This in turn will contribute to the loss of cellular function and diseases finally ending in aging. The paper also discusses how lifestyle contributes to DNA methylation patterns along with diet, exercise, and exposure to environmental toxins. An unhealthy diet and sedentary lifestyles have, for instance, been said to accelerate DNA methylation change and therefore increase biological ages. However, certain pharmacological and targeted interventions in caloric restriction, to mention exercise, show dampened and decreased reversal of these changes, promoting a biological young age. This has huge implications in research on human health, observed Sinclair, asserting how this technology can possibly measure a person's biological age in a clinic while offering him or her an anti-aging treatment as well as monitoring it. Needless to say, doctors would therefore be in a position of using the epigenetic clock as a tool that will track every change in the biological age of a patient after a person makes alterations to his or her lifestyle, consumes drugs, or undergoes any type of health intervention. In other words, the health management could end up being very personalized. Further, the epigenetic clock could revolutionize the way we think about aging and disease prevention. Identifying those whom are aging at a faster rate than would be suggested by their chronological age could allow us to intervene in such aging so as to prevent or delay age-related diseases. This approach can move the medicine's focus from curing diseases after their appearance to prevention prior to the onset. Sinclair also flags the ethical and social implications that the manipulation the epigenetic clock may have. Exciting as increasing healthy lifespans represents a line of inquiry into the potential impacts it will bring. For example, with much larger lifespans, what will that look like regarding the population, resource availability, and the economy? How is the society going to care for inequity regarding access for life extension technologies? The chapter concludes with the research future of aging. As Sinclair says, we truly need to take an advance further on the epigenetic clocks of aging. Definitely hopeful that once we start understanding the epigenetic clock more deeply, new ways to extend human life and enhance the quality of one's life length critical ages will be found alive. Chapter 4: Resetting the Clock. Chapter 4, David Sinclair now introduces the innovative idea of resetting the clock, which means reversing back the biological age of a cell, tissue, and even whole organisms. In this chapter, he gets into the mechanisms and scientific breakthroughs that function together to turn back the biological clock, for the tantalizing possibility of not just slowing aging but reversing it. He discusses various strategies and technologies that have shown promise in resetting the epigenetic clock to youth. At the root of resetting this clock lies the idea of biological reprogramming. According to Sinclair, every cell in the body contains a quite identical DNA, but very different functions are performed by these different cells: the skin cell, the liver cell, and the neuron. A record of genes that are on or off in any given cell is maintained through what is called the epigenome. Closing in on epigenome disorganization over time, cells age, leading to loss of cellular identity and function, one of the major drivers of aging. Biological reprogramming resets the epigenome back to a more youthful state. In basic terms, it erases all the accumulation of epigenetic marks that happened during most of one's lifetime and returns the cell back to its more original, youthful program. Sinclair likens this to taking an old, worn-out machine that can be restored to pristine condition by replacing or repairing worn-out parts. Much of the chapter is dedicated to the discovery and consequences of the Yamanaka factors, 4 genes that can actually reprogram adult cells back into a state of pluripotent stem cells. It is quite ironic that this discovery brought Shinya Yamanaka the Nobel Prize in 2012 for showing that it is possible not only to take mature cells, but also reset them into a state very much like an embryonic stem cell. Sinclair describes how the Yamanaka factors changed our notion of cellular aging. By activating these factors, one reviewer turns off, almost at least to Ellen, the hallmarks of aging, the biological clock of the cells, returning them to a more youthful state. Such induced pluripotent stem cell technology has opened new avenues for regenerative medicine, allowing for damaged tissues and organs to potentially be regenerated. While full reprogramming to a pluripotent cell state has some advantages, it comes with a huge risk that include uncontrolled cell growth and cancer. Taking this further, Sinclair pointed out a conceptual solution in the form of partial reprogramming. That was transiently activating the Yamanaka factors for a short period of time, adequate for a resetting of the epigenome, but without completely erasing the identity of a cell. Partial reprogramming has also shown conceivable results in animal studies. Sinclair says, pointing to experiments where all the mice were partially reprogrammed with dramatic results, tissues rejuvenated and an expression of symptoms of aging significantly reduced. He mentions, for example, that when they apply this result to aged mice treated with this technique, one sees enhancement in muscle strength and kidney functionality, and the restoration of vision in cases of age-related blindness. Besides genetic reprogramming, Sinclair writes about the role of sirtuins, proteins involved in regulating cellular health and longevity. As crystallized in earlier chapters, sirtuins play a central role in the preservation of epigenome stability against age-related damage. Their activity declines with age, hence their contribution to the aging process. Sinclair introduces the molecule NAD+, the nicotinamide adenine dinucleotide, required to activate sirtuins. As people age, levels of NAD+ drop, and with them, sirtuin activity goes lower. The idea here is to boost NAD+ levels, increasing the activity of sirtuins and, in so doing, potentially reset the biological clock of cells. The chapter describes several approaches to elevate NAD+ levels, including supplementation with the NAD+ precursors, such as nicotinamide riboside or nicotinamide mononucleotide. Such supplements have been very promising in preclinical studies. Whole enables restitution of decreased NAD+ levels, improvements in mitochondrial function, and lifespan extension in animal models. Sinclair gives a positive review on how the like possibility may exist to reap this value, to reset this clock in humans. He rolls out a plethora of ongoing research and clinical trials that are testing safety and efficacy methods of reprogramming technologies in humans. Though the science remains early, thus far it seems very promising, suggesting that it may be possible to develop therapies that can reverse aging and extend the human lifespan. He did, however, express the obstacles and ethical dilemmas associated with such technologies. The reprogramming of the epigenome is tremendously complex and requires stringent control lest unintended results, such as cancers, occur. There are also larger social concerns to be factored in, for instance, prolongation of the human lifespan regarding population increase, distribution of resources, and the ordering of society. This raises deep ethical concerns in relation to the potential to reset the biological clock. Sinclair wrote as an important social consideration the careful weighing of the long-term implications for faculties that have life-prolonging technologies. How is society to adjust to such wide discrepancies in accessibility? What would it foreshadow for world demographics and availability of resources should humankind start to live radically longer? It means Sinclair is calling for a balanced approach to the development and implementation of these technologies. He calls for rigorous scientific research, open public discourse, and setting up of the ethical guidelines that will allow the benefits to be realized from life extension in an equitable and sustainable manner. The chapter concludes by looking at the future. Sinclair believes that we stand today at the threshold of entering into a new era in medicine in which the aging process takes the place of many other diseases, at least partially reversible. He projects a future in which reprogramming technologies will join the authors and become regular parts of healthcare, rendering everybody empowered to stay young and vigorous well into advanced age. However, Sinclair is still very much aware of the hurdles lying ahead, considering aging science is so complexly complicated. Indeed, he had remained hopeful that, with further research and innovation, we would soon reboot its biological clock fully and unlock eternal youth. Chapter 5: Survival of the Fittest. In Chapter 5, David Sinclair tries to go deep into the evolutionary roots of aging and how survival of the fittest has sculpted the way any organism ages, not excluding humans. He gives insight into the hypothesis that aging is not something random but very inherent in our biology, both influenced by the principles of natural selection. He explains how our contemporary environment and lifestyle interact with these ancient evolutionary mechanisms, often accelerating aging. Sinclair opens the chapter with a discussion of how, from an evolutionary perspective, aging is not really an issue for natural selection. Evolution basically selects for early life traits that convey advantages in survival and reproduction and assures support of these genes into the next generation. Inevitably, right after successful reproduction, the pressures of natural selection become weakened, and those mechanisms responsible for maintaining cellular and genetic integrity start falling apart. As a result of this failure, progressive accumulation of damage starts to take place and eventually leads to senescence. He discussed the theory of antagonistic pleiotropy, according to which genes whose actions are favorable early in life have unfavorable effects in old age. For example, genes associated with growth and reproduction might be quite useful during youth but contribute to the acquisition of senescence and senescence-related diseases. In this way, the trade-off is brought into focus as being a central theme within evolutionary theory on aging. Sinclair puts forward the reasons that in the wild, conditions such as predators, lack of food, and unfriendly environmental conditions cause stress in organisms. This plays a major role in the evolution process since only the fittest of them survive to reproduce. Because of the process of natural selection, currently available mechanisms at genetics and cellular levels provide organisms with ways to cope with stress through DNA repair, maintenance of cell health, or fighting oxidative damage. However, very many of these stressors are significantly minimized or eliminated in today's society, according to Sinclair. Immensely easing these stressors has not only resulted in longer life expectancy, but also lessened the environmental pressure that once kept our bodies at an optimum level. The outcome is that the mechanisms engaged to shield us from aging-related damage at the present moment are no more as energetic and effective than they used to be in our forefathers. It then discusses the ways through which the modern environment, with abundant food, low levels of physical activity, and reduced impacts of environmental stress, interfaces with our evolutionary biology to promote accelerated aging. Many of the lifestyle factors associated with aging, poor diet, lack of exercise, chronic stress, are relatively new developments in human history, says Sinclair. Our bodies have not had the time to adapt to these changes, leading to a mismatch between our biology and our environment. For instance, the high intake of high-calorie and industrially processed foods might overwhelm the body metabolic systems and lead a person to obesity, diabetes, and other diseases related to old age. In the same way, sedentary life in today's society reduces the demand for the body to maintain its muscle mass and cardiovascular health apart from physical decline with aging. Sinclair follows up on the concept of hormesis mentioned in previous chapters, suggesting that mild stressors such as caloric restriction, exercise, and cold would be beneficial for prolonging life. Endogenous mild stressors should induce the pathways related to survival and further improve the cellular mechanisms of repair, therefore boosting health maintenance. This segment of the chapter now focuses on the molecular pathways for hormesis, including the activation of sirtuins, AMP-activated protein kinase, and production of heat shock proteins. Sinclair argues that if we dose ourselves with controlled amounts of stress, then we can actually mimic those stresses that our ancestors went through, reactivating ancient survival mechanisms that were set in place to protect against aging. Another key concept in this chapter is the thrifty gene hypothesis. The author explains that genes which, from the perspective of evolutionary biology, were advantageous in conditions of low food density became harmful today under conditions of abundance. For example, genes that enhance the storage of fat and make it easy to get energy out of food would have been useful for our ancestors in surviving states of famine. Whereas in an environment where there is plenty of food and it is easily available, these same genes may result in obesity and metabolic syndrome. Sinclair describes how knowledge of the role that these thrifty genes play can help in finding strategies against their adverse effects today, that is, dietary interventions, exercise, and probably genetic therapies would soften the blow of genes on health during senescence. The authors further introduce one for the disposable soma theory, which suggests organisms have to divide their resources between reproduction and maintaining the body, or the soma. In this view, the theory states that since evolution is mainly concerned with propagating genes into the next generation, more resources in an organism are pushed towards reproduction than in maintaining the soma. As a result, the body becomes disposable after reproduction, and this is what forms the basis for gradual decline with age. Sinclair explains how this theory sheds light on the fact that some species, usually those with relatively shorter lifespans, basically rush through the aging process right after the stage of reproduction, while those with longer lifespans tend to be further invested in somatic maintenance. He also cites how modern medicine and technology can possibly tilt this balance toward humans being able to maintain their somatic health for a longer period and, in essence, extend life. He concludes the chapter by suggesting what these evolutionary concepts have to say in respect to human health and longevity. The message he carries forward to his audience from this long history is that while our evolutionary past determined the way in which we age, not necessarily we are enslaved by it. Through scientific advance and technological progress, we can act on aging processes and even change the course of evolution itself. He brought out the main points of embracing lifestyle choices that align well with our evolutionary biology, the inclusion of regular exercise, a well-balanced diet, and periodic exposure to mild stressors. Moreover, he does mention that in the near future there might be medicaments with the capability to target mechanisms related to aging that have the potential to lengthen both life expectancy and health span. Sinclair believes in a future with central evolutionary medicine, one that takes into account our entire evolutionary history to understand health and disease. By explaining to everyone the evolutionary roots of aging and diseases, more effective interventions will be made, which will not only address symptoms but are also directed against the causes of aging. With further insight into the genetics and conditioning of aging, he thinks that intervention will be tailored to individual needs. This will give rise to person-oriented anti-aging therapies for maximum health and longevity. Chapter 6, The Age of Innovation, Chapter 6 of Lifespan, Why We Age and Why We Don't Have to by David Sinclair, talks about different novel technologies and how they can change the paradigm of the discipline of aging and longevity. Chapter 6, In the Future, Technologies that Will Change Aging, looks into the deep seeding of biotechnologies, genetic engineering, and other breakthrough advances that scientists are talking about with regard to not just arresting the process of aging, but actually turning it backward. Sinclair puts the emphasis on the real power that innovations have to bring change and discusses the profound consequences that are possible for man as an individual and society at large. Sinclair begins his narrative with the pace of changes in biotechnologies, particularly gene editing, stem cell research, and further regenerative medicine in this scientific field. He explains that these technologies have been starting to empower scientists to manipulate the very basics of biological processes and probably to affect the very course of aging. Most noteworthy among the important breakthroughs in the chapter is CRISPR-Cas9, an innovative technology in the area of genetics which makes mutation changes in DNA with stated accuracies. It explains how CRISPR could be put to use to make alterations to portions of one's genetic code that predisposes one to age-related affections or to upregulate cellular activities responsible for protection against aging. He touches on the use of CRISPR in germline editing and how this could be utilized to correct genetic defects in an embryo, avoiding the manifestation of some diseases. But even as the discussion of CRISPR progresses, Sinclair continues, there are other genetic engineering threads that are brought up to age gracefully. Much of this has to do with gene therapy. The idea is to transfer specific genes to a patient's cells to replace the missing or defective genes that are causing their particular disease. Already, this particular method is coming under some useful views for specific genetic diseases. Scientists are now researching it for its ability to extend life. He elaborates on this potential in epigenetic reprogramming, resetting the biological clock of cells through the changes enforced on their epigenetic marks. By reprogramming the epigenome, the scientists dream to restore the cells to a younger state, which in fact will reverse the aging process. This is an outgrowth of the findings discussed in chapter builds on recent work as expressed by BOF, so should it be expressed by you as reducing fear and skepticism of research that takes into account man's drive to fabricate means to dictate everything, even his existence is a process of deterioration, an act considered an effort to play God himself, which defiles his essential being. The last significant innovation this chapter encompasses is concerned with regenerative medicine, which repairs or replaces damaged tissues and organs through stem cells and other superior therapies. Sinclair elaborates on how treatments based on stem cells are worked out for the purpose of tissue regeneration, such as heart muscles after a heart attack or nerve cells in neurodegenerative issues like Alzheimer's. He also explores the area of tissue engineering, where researchers are generating artificial tissues and organs in the lab. These bioengineered tissues could, in the future, replace failing organs in older people and thereby relieve the scarcity of available donor organs. Sinclair points out advances in this field that include recent work on creating 3D bioprinting techniques for the generation of complex tissues with architecture that must be under high resolution to be functional. Sinclair then impressed upon it the importance that other pertinent contributions had already been made by artificial intelligence, technology, and big data in hastening this pace of innovation in research on aging. AI aids in the sorting through reams of biological data for meaningful patterns and connections that a human could never begin to unravel. AI capabilities have helped to reveal new targets for therapies intended to ward off aging and optimize the existing treatments. The implementation of AI is also making it possible to create mechanisms to provide personalized medicine, wherein individual-specific treatments can be modulated based on his or her unique genetic and epigenomic identity. In Sinclair's words, it literally integrates big data together. He expects that artificial intelligence will eventually tell the likelihood that a person has the capacity to develop any particular age-related disease, advise about specific interventions that a person might take, and take some active steps to reduce their risk. Therefore, this extension of the lifespan and health span by such personalized medicine may be dramatic in the future. The next big area that Sinclair believes has a lot of room for innovation in aging involves pharmacology. He goes on to discuss the development of pharmacological intervention that targets the molecular pathways involved in aging, sirtuins, AMPK, and mTOR. Such measures, on the rare occasion known other than to a specific researcher as geroprotectors, are replicated in relation to the benefits brought through the ways of calorie restriction and other lengthening life practices on the molecular level. He points out a few hopeful compounds currently under testing, such as resveratrol, metformin, and rapamycin, each of which has been found to prolong life in animals and is currently being evaluated in human clinical trials. This represents a giant theoretical shift in paradigm that such drugs could be used preventatively in the healthy. The chapter also deals with the societal impacts of such technological advancements. Also, he recognizes that while the innovations being developed at his laboratory hold out the promise of a radically increased human lifespan, the work also brings some very important ethical and social questions to the table. For example, how will an aging society accommodate the challenges presented when those aging within it live orders of magnitude longer than have heretofore been the case? What is the resource and employment implication for society and social structure? Sinclair perceives that though these barriers mesh mountain high, they can be raised down sometimes with the sense of planning and policy frame making. He opines that all the benefits of increasing the human lifespan, including reducing the amount spent for diseases and adding quality to the human lives, are much more than the expected disadvantages. But he feels the essence should be seen that these technologies are not at the disposal of a few rich and elite people only. He closes this chapter on an optimistic note, outlining the promising future these aging research innovations hold for the health of humans. According to him, we are at the brink of a new age in medicine, where there will no longer be inevitable decline caused due to aging, but a condition that is noticeable and treatable and can even be reversed. Sinclair calls for continued investment in research and development, as well as collaboration between scientists, policymakers, and the public to ensure that the benefits of these innovations are realized in a way that is ethical and equitable. He envisions a future where people can live longer, healthier lives, free from the debilitating effects of aging. Lifespan, Why We Age and Why We Don't Have to, concludes with a powerful message of hope and possibility. David A. Sinclair's exploration of aging challenges us to rethink what we know or think we know about getting older and the possibilities of extending human health and lifespan. By weaving the cutting-edge science together with vision, Sinclair unfolds a future that is not one of inevitable decline, but one of a condition over which we have control and possibly of one from which we can escape. The book made readers accept these sciences and wonder about the transforming effects in the realms of life and society. It opened a view of hope onto the future, when we might be enjoying long, very much, and healthy and satisfying lives.